Hi, this is Roman, and today we're going to be going over Unit 8 on conditional probability, Day 11, Combining Events, Part 1. How can we use the addition rule to calculate probabilities? So I'll be doing a few samples today, and the first thing that we're going to look at is the idea of two events being mutually exclusive. And we're going to define that as if there are disjoint or they cannot both occur at the same time. So here are the rules for the addition rule. The probability of A or B is going to be given by the probability of A plus the probability of B minus the probability of A and B. But if A and B are mutually exclusive, or they cannot occur at the same time, then the rule can be simplified to the probability of A or B equals the probability of A plus the probability of B. And we're going to talk about how we're not going to memorize two different rules, and we could really just focus on this first one. So let's take a look at a sample. So sometimes these rules don't make that much sense when we're using our intuition. So here we have the probability of drawing a king or a heart. So as we highlight here our sample, I could see 4 kings. And then in terms of hearts, I see 13 cards in this deck that are hearts. So I could do 13 out of the 52 plus the 4 out of the 52. And then I see this overlap that I'm going to subtract, or 1 over 52. Now, if I'd like to, I could always use my Desmo scientific calculator as I type that in. And it's a great, useful tool. So I'm going to type in 13 over 52 plus 4 over 52 and minus 1 over 52. That gives me my answer. If I want to click this fraction bar here, it'll simplify my answer as 4 over 13. And with this real life example, we're really able to reason our way through it, right? We might not even notice that this is the probability of drawing a king plus the probability of drawing a heart minus the probability of drawing a king and a heart. And notice that that's not mutually exclusive because that can occur at the same time. So we have to subtract that out. All right, let's take a look at another sample. The probability of rolling a 1 or a odd number. We're going to notice that in this case, a 1 is an odd number, right? So sometimes in these real life samples, we could really use our intuition, right? So if we just circle the odd numbers, 1, 3, 5, and I already circled 1, that really tells me, well, man, this is 3 out of 6 or 1/2, right? And if I do the probability rule, the probability of rolling a 1 is 1/6 plus the probability of odd, which is 3/6, minus the probability of odd and the 1, which is 1/6. That brings me back to 3 over 6 or 1/2. Again, the rule doesn't necessarily have to be memorized here. We could really use our intuition. So let's take a look at another sample here. Rolling a 1 or an even number. Well, the probability of rolling a 1 is going to be 1 out of 6. The probability of rolling an even number is 3 out of 6, right? And if I circle them, I have 1, 2, 4, 6. I got those 4 options. This gives me 4 out of 6. Or if I divide on top and bottom by 2, that would happen 2/3 of the time. Now, in this case, we see that we're really only doing the probability of the first event plus the probability of the second event, but I'm going to say that we're still subtracting out the probability of A and B. And the reason I could say that is because 1 and an even number, they can't occur at the same time. So the probability of A and B, in this case, is 0. And we simplify that by just not writing it. So it's not a completely new formula. And that's an important fact to identify here. Now, let's try an example where our intuition can't necessarily be used, and we actually have to know the definitions. So in this example, we're asked to consider an experiment with events A, B, and C for which the probability of A is 0.23, the probability of B is 0.40, and suppose that the probability of C is 0.85. I got these three events. A and B are mutually exclusive, and events B and C are independent. So we have to know the language here, right? We cannot use our intuition. There's nothing here given for our intuition. There's no deck of cards and there's no dice. So in this case, since we're told that A and B are mutually exclusive, for the probability of A or B, that's going to mean that it's the probability of A plus the probability of B. And in this case, we're told the probability of A is 0.23 plus the probability of B is 0.40, so our answer is 0.63. Now, I do want to remind you that doesn't mean we don't have minus the probability of A and B here. It's just since they're mutually exclusive, these can't occur at the same time, so this happens to be a 0, right? And if we do 0.63 minus 0, we still get 0.63. So that was a sample for A and B being mutually exclusive. Let's take a look when it's not. So same question here, but now we have the probability of B or C, right? And let's see how we would go about this. So the probability of B or C is going to be the probability of B plus the probability of C minus the probability of B and C, since B and C are independent events. So now we know the probability of B. We're given that that's 0.4, and we're told that the probability of C is 0.85. Now, how do we simplify this probability of B and C? Again, our intuition might be a little bit hard here because we don't have something in real life that we could grasp. So we have to know the rule that the probability of B and C is equal to the probability of B times the probability of C. And now we have the two numbers here, right? So we're adding the probability of B and C minus the product of the probability of B and C. And now this will simplify to 1.25 minus 0.34 equals about 0.91 or 91%. And just to finish off, I'd also like to model how I might want to show this using a Desmos calculator as well, right? So if I do type in 0.4 plus 0.85, and then I want to subtract the product here of 0.4 times 0.85, I get my same answer here as 0.91 or 91%. So this was a sample of the addition rule with examples of intuitive questions and then questions where your intuition would not lend itself to solving the answer.